Hello, I'm Gavin Rowland, the project lead for ASU's Charlotte team, and I'm going to introduce some of the technical validation and demonstration information. And so in this presentation, I'll introduce some of the validation testing, including the laboratory and simulation tests and the Earth analog tests. We'll start off with the laboratory and simulation tests. The first category of test is the thermal operation tests. These were designed to test all of the critical thermal systems of the rover at a component level. So to start, we have the thermal breakfoot. This device is designed to thermally isolate the rover body from the lunar surface so that extreme temperatures of the lunar surface don't dramatically influence the thermal system of the rover. This test was designed to determine the thermal conductivity of the foot as a thermal resistor and compare those to simulation results. The test was very successful, and the simulated values were close to the test values. The radiator test was designed to determine the thermal transmittance of the radiator and compare that to the predicted values in simulation. This is important because the radiator is the only way for the rover to shed heat. The tether test was designed to simulate the thermal divide between the lunar PSR and sunlit region. This test was successful at cooling one side of the tether and heating the other, and to determine the survivability of the tether. Thermal cycling tests were conducted to expose the subassemblies to approximately lunar temperature swings. This was to test for any cracking and structural survival. As you can see in the figure below, the thermal cycle tests match with the lunar data fairly well on the high temperature end, but fall short with the low temperatures, as we are only using liquid nitrogen and our thermal chamber was custom for the oversized DUTs, and the thermal chamber leaked heat. We also conducted dust testing in a lunar sandbox with lunar regolith simulant. We walked the rover back and forth with several shoe designs, including a hoof shoe and an Apollo shoe. The hoof shoe provided excellent grip for extremely soft regolith. We also tested the abrasion of the Kevlar sleeved tether. The abrasion tests were conducted in order to determine the lifetime of the tether if it rubs against a rock at the presence of lunar regolith, and it was determined that the abrasion of the tether is a serious risk, although under normal mission circumstances it is unlikely that the tether would be exposed to such extreme conditions. It would be worth trying to find better solutions to resist abrasion. Medium voltage direct current electrical tests were performed before and after the tether was thermally operational in the TVAC chamber. This is to test the coax cable under 500 watts of power transmission at an operating voltage of 8 to 10 kV. We tested the untampered cable beforehand in the first medium voltage test, and after the cable was thermally stressed, we tested it again to ensure that no cracks formed in the dielectric of the coax cable. These tests were both very successful, and the thermal stress of the tether did not lead to any failure from high voltages. Vibration testing was left incomplete per the team's risk management system. This is because of timeline constraints from supply chain issues. The vibration testing provided the highest risk item with a mismatched TRL contribution. That is to say that this version of the rover, this prototype, was specifically designed for Earth analog testing without a microgravity harness. So a lot of the assemblies are a lot heftier than they would be on a lunar version. And so vibration testing would not specifically advance the TRL because this is a Earth version. Now we're getting into the Earth analog tests. So for the phase 2A, Earth analog tests were for locomotion and software, as well as navigation planning. These tests included darkness testing and terrain testing at Hayden Butte next to ASU, and terrain testing at Colton Crater in Flagstaff, Arizona. So darkness testing was conducted in ASU's drone studio, and this was done to determine the effectiveness of the lighting system of Charlotte, because it's very important for navigation in the permanently shaded region of the lunar surface. We recorded the HazCam and NavCam data during testing to determine the camera position validity compared to the lights. So that darkness testing footage was real time at the speed of the rover, and as you could see, it was turning in place. The other piece of Earth analog testing was for locomotion, the first of which was located at Hayden Butte next to ASU, and this was for uphill and downhill traversal testing with several large rocks and also small gravel. This test provided some extreme slopes that, although they weren't very lunar analog, they were much more extreme than you'd see on the lunar surface. And so this provided a good platform to test Charlotte's locomotion abilities. The final Earth analog locomotion testing was conducted at Colton Crater in Flagstaff, Arizona, and this terrain is very close to what you'd see in a lunar crater. We conducted both daylight and darkness testing with an analog PSR as the shadow of the crater approached the rover as it was traversing into the crater. We traversed a total of 275 feet downhill, 50 feet uphill, and 25 feet of omnidirectional traversal.